In this experiment, we studied the draining of a water tank through a small hole and compared our experimental results with the theoretical prediction given by Torricelli's law. The objective was to measure how the exit velocity changes as the water level decreases and to evaluate how well the ideal theory describes the real flow behavior.
From Bernoulli's equation, assuming non-viscous flow, a small hole, negligible surface velocity, and atmospheric pressure at both the free surface and the exit, the velocity of the exiting liquid is given by U is equal to root 2gy. This relation predicts that the exit velocity depends only on the height of the liquid above the opening.
Our experimental setup was intentionally simple. We used a transparent plastic bottle and created a small circular hole. The bottle was placed on a kitchen top filled with water and the hole was initially sealed using tape. At the start of the experiment, the tape was removed, allowing the water to drain freely, while the scale continuously measured the mass of the water remaining in the bottle as a function of time. This setup allowed us to indirectly track both the water level in the tank and the flow rate.
Using the known density of water, we converted mass measurements into volume. From the change in volume over time, we calculated the volumetric flow rate, and dividing by the hole's area gave the experimental exit velocity. Assuming the bottle has a constant cross-sectional area, we also converted the remaining water volume into the instantaneous water height inside the tank. These plots show the measured exit velocity over time for two different hole diameters. As the water drains, the height difference between the free surface and the opening decreases, leading to a reduction in hydrostatic pressure at the hole and therefore a lower exit velocity. In both cases, the velocity decreases over time, as predicted by the theory. The larger hole drains more quickly, while the smaller hole exhibits a longer and smoother draining process. In both experiments, the theoretical prediction consistently lies above the experimental data, indicating the presence of viscous losses and imperfections in our hole boundary, which are effects that are neglected in the ideal model.
By introducing a discharge coefficient, we obtained the average values between 0.5 and 0.6, which are typical for sharp-edged holes. Agreement with theory is better at early times and for the smaller hole, where the small hole and quasi-static assumptions hold more closely. Deviations increase at later times as the flow becomes more unsteady. Overall, our results confirm the validity of Torricelli's law as the first-order model, while clearly demonstrating the limitations of its underlying assumptions in real fluid flow. The small hole assumption breaks down when the hole becomes comparable to the water tank dimensions, leading to unsteady flow and behavior closer to a falling water column.